In this video, I will show you how you can take any image and encode it with a file, so secretly encode this data into it. The resulting output will be a normal image, and you can actually decode it using special software that we will also write, and you will be able to recover this original text. Of course, the size of this file is defined by how large this image is. But that's the only limitation that you have. You can encode any kind of file into it, basically. So the way that we will be doing this is the following. If you think about the image, it is just there are numbers that represents the intensity of the red, green, and blue values of a particular pixel. So here I've represented a case of the color white, which has the maximum amount of red, green, and blue, and of course when you combine this it appears to be white. 255, by the way, is the maximum number that you can have, and so the numbers go between 0 and 255. Now if you were to change the highest significant bits of the number, you would of course change the color very much, and this change would be very visible. However, if you consider these least significant bits of the pixel, changing this wouldn't change the color too much. It's like instead of having 255, let's say the last two bits can have a maximum value of 4. So 1 and 2. So the maximum change you can have is 3 if you were to change these values. So we can only have a very minor change if we were to use these 2 bits to encode our data. So that's exactly what we will be doing. We will take our file and basically put the bytes, break it down into 2 bits at a time, and then replace these with the bits of our file. And on the decoder side, we will retake these last 2 bits and then assemble them together to get the original file back. And this will be, the modified image will be a completely valid image. There is nothing wrong with it. There is no extra code, nothing. There is just a normal image with valid pixels, and that's all. Okay, so let me first show you how this program works. Here, this is the Python script that we will write together later. But the way that it will work is that you can take anything, any file or any image. In this case, we are taking an image of a dog, and we can encode this on top of this image, and the output will look pretty much exactly like this, but it will have this data encoded into it. Of course, as I mentioned before, the file size is limited by how big this image is, so that's the only restriction. Now let's try to do that. So we have Python and this name of the script. Then we have to pass in the data the file that you have to encode. In this case, it will be dog.jpg. This one is hard-coded in the script, so don't worry about that. And the output will be, for example, okay, let's just call it example. And that should be, okay, one thing you have to do is pass the encode or decode flag. In this case, since we want to encode, we have to pass -d. And now let's wait for it to encode. Okay, so it has done that, and as the output, it has generated this file. Now I can also permanently delete this, and I will still be able to recover it from this image. So this is the output that we get, and this is the original one. So the original one is this one, and they look very similar actually. So now let's actually try to decode it. So I will use the same program. The only thing I will change is instead of encode, I will pass the decode flag, and then I will pass the name of the file that we generated previously. So that would be example.bmp. So as you can see, I already deleted it. Okay, so I do have to pass. Yeah, I had to write a in front of it. So that's actually a bug in the program, but it's okay. So now you can see that not only the image was regenerated, but also the file name was preserved. This one is just a padding. This is something to do with the way that I store it. But stored the name of the file also inside the data. But as you can see that we have successfully recovered the image. And this is not restricted to only images. You can encode anything. You can even encode the program that I wrote. And actually, let's try to do that. So I will encode the program itself, encode.py, and let's call it example 2. Right. So you can see I will not delete it in this case because I don't want to accidentally lose it, but you will have to trust me on this. So I will decode example 2, and yes. Alright, so here is the code, and we can try and open this as well, and you can see we have it here. Okay, so I've opened up a new file here, and I will be programming from scratch so that you can follow along better instead of just showing you the code that I've written. We will be dealing with images and arrays, so let's import first the two libraries that will be required. So import numpy as np, and also from below import image. And the first thing I need to do, first let's just take the image, write some data into it and save it, and make sure that we can read it back. This of course is important. This will only work if we save the data, save the image in a lossless format. Otherwise compression will completely destroy our data. So let's make sure that that is working. So I will import the image dot open, and then I will pass in the name of the image, which will be image.jpg, and then I will convert it into a numpy array is equal to numpy.array, and then you can just pass in the image file, and then let's just see what is the value of the image at the location of 0, 0, 0, 0, and now we will modify that value image and 0, 0, 0. Let's make it 99, and then we can save it back. So before we can save it, we need to convert it back into the image, the pillow image. So image dot from array, and we will have the image here, and now we can save it. So image dot save, and the name will be image.bmp. Now this is important because BMP is a lossless format, and then this way our data will not be corrupted. Now just to make sure that everything works fine, I will load it back, but instead of now loading the original image, we will load back the image that we just modified. And this, if it works correctly, we should see, the first time we printed, we should see whatever value it originally was, and then in this time, the next time we would see the value that we saved here, which was 99. So okay, image JPEG file is not scriptable. This is print image. Okay, so I think this is supposed to be n is equal to an auto minus. Alright, so yeah, okay, so now you can see that the first time it was on 35, which was the original value of that pixel, and now we have modified it successfully. So this part is done. Okay, now with that done, let's write the two functions, the two primary functions. One of them will be encoding the data, and the other one will be for decoding the data. Let's create two functions, write data, and this will take the image, then the data that we want to encode. This will come from the file, and the file name, and because we have to file name, because we have to encode this as well inside the data. So that's the first thing. And now the first thing we need to do is create an empty byte array, and I'm creating a byte array because we want to manipulate it. If we just use bytes, we can't change the size, so I will just take a byte array, and this will be equal to byte array. And the next thing I want to do is I want to add the file name as the first 12
first 12 bytes of this data, because I want to also save the file name inside this thing. So for that, what I will do is extend it with the file name, but of course encoded in binary. So we will have byte array dot extend, and extend just actually adds a bunch of um, bytes together, and the bytes that will be basically the file name, but we have to write justify it. And the reason is because in this case the alignment is very important. So I will just take the first 12 bytes and assume that this is the file name. So even if our file name is shorter than that, we have to pad it to make sure that that is exactly 12 bytes, because otherwise our alignment will be all wrong. So I will write justify it, and then this will be 12, and I will pad on the right with the, it can be anything, but I'll just use 0, and the encoding that we will be using will be UTF-8 encoding. Next thing I need to do is to add the file size, because when we are reading the data, we need to know how much bytes we should actually read. And for that, we can just take the length of the data. So we have length of the data that is coming from here, and then we have to convert it to 2 bytes, because we are saving it as bytes, and 4 bytes are enough, because 4 bytes, this would allow like 2 raised to power 30, this will allow like 4 gigabytes of file size, which is way more than we would need. So little endian encoding, if you don't know what is little endian, you just really don't, you don't really have to know that. And then we will extend it to our byte array. So we will have byte array dot extend so far we have in our byte array the file name, then the amount of the bytes of the file size that we are going to add, and then finally we will have to pass in the file itself. So byte array dot extend, and then finally the data. And now we have to store it in our image. So for the image, we need to know the height, width, and the channels, because you will be iterating over it. So height, HEIGST, width, and the channels is equal to the image dot shape, and the data size, sorry, I don't want that. Why is it adding? I don't want your help. So the data size is equal to the length of the byte array. So now this is the length of not only the original data, but also the data that we have added. I mean, to be honest, this is plus 16, but anyways, we can just check it like that. And now we have to add, now we have to basically put it, so we have to split our data into 2 bits at a time, and then just add it to our original image. So this is how we will do it. We will create 2 variables called byte number. So this will be the byte number of our data that we are writing, and we will start by 0, and then we will have a nibble. I mean, it's not exactly a nibble. This represents the number of how can I say, the 2 bits, but the identity of 2 bits. Let me try to explain. So if we have a byte which has 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, we need to store 2 at a time. So we need a way to identify which one is that. So for that, even this is not exactly a nibble, because nibble is defined differently, I think, but I will just call it as a nibble, and number perhaps would be okay, and I will call it 0. And okay, so now what we need to do is we need to iterate over all of the basically all of the different pixels of our image. So I will create a nested for loop. So for I in range 0 to the height, then for j in range 0 to the width, and finally for C in range 0 to channels. And now what I will be doing is taking the image and I, comma J, comma C, and this part may be a little confusing, but I will try to explain it to you. So what we are doing first of all is taking our image. First we have to take out our nibble, the specific part. So if our data is like this 0 0 0 0 0 0 0 0, we have to take our specific part. So that one will of course be the from the byte array. We have to take our specific byte, so that will be the byte number, and then we have to shift it down by the amount of the nibble multiplied by 2. And so what we are doing is that, let's say we have 100 bytes or whatever bytes, this part just takes that specific byte, then we shift it down by the nibble by 2. So let's say if we were in the first case, if this is our nibble, it will just shift it down by nothing because this is 0. Remember, this is actually 0, so this will not change. However, if you are taking the first one, then you will shift it down by twice. So then the thing in this position will actually be this one. The next thing you have to do is to AND this by the number 3, and it by the number 3, 0x03, and ANDing basically will clear anything that is behind this nibble, and it will just 0 it, because 3 hex is actually something like this, 1 1. So whatever data is here will be gone, so we don't really care about that. Then we have to take our original value and we have to clear out the last 2 bits, and we have to make space for the data we will be entering. So we have to bitwise AND it with 0xfc, which is exactly the opposite, which is like this one. It's 1 1 1 1 1 1 and 0 0. So we will take that one, and then we need to OR it, because what OR will allow us to do is that since we have already cleared this will be 0, and OR will just copy that part and put it here for us. So that part is good. The next thing we have to make sure is that we have to change the values of the byte and the nibble correctly. So what we will be doing is that the nibble will always increase. Every time we change, it will increase. But once it reaches this one, it will roll back over here. So it will start with the 0, the first, the second, the third, and then we'll go back. So we can do it like this. So nibble number, and let me make sure that I'm actually all right. So nibble number, and we will plus is equal to 1 all the time, but also we will take the modulus of it. Modulus is equal to 4. So when it reaches 4, it will go automatically to 0. So this is exactly what we're doing here. And then we have to make sure that whenever we finish the whole byte, we should update it, and we should start working on the next byte. So if nibble number is equal to 0, this means that whenever this happens, this means that we have fully written that particular byte, and we can move on to the next one. So we can say that byte number is actually plus equal to 1. We can increment it. Plus equal to 1. And in case we have written all of the data, we just want to return from our function, because, well, there's no point in writing any further. So we will say if the byte number is actually greater than or equal to the data size, we just will return from this function and not bother with doing anything else. So this is the function that we will use for writing the data. Similarly, we can write the function for reading the data, and it will be very similar. So let me actually just copy it. This one I will just copy from my old function because it's a little bit more complicated, but I will explain what I'm doing here. So this is the function, which is the idea is very similar, but I've done three things here. So I have 3 byte arrays. One of them is actually for the file name. As you remember, inside the data that we actually store inside our image, we have 3 things. We have the file name, we have the file size, and we have the data itself. So here we have created 3 byte arrays. Then of course we take the image again, and now here data size represents this represents 16, and I will tell you why. Because the first 16 bytes for sure will not be 0, because they contain, the first 12 contain the file name, and the next 4 contain the amount, the number of bytes of the data. So we first of all assume that there are only 16 bytes, and we read all of them. When we are below 12 bytes, we store all of that data inside our file name byte array. And for the next 4 byte, we store it inside our file size byte array. And then what we do is that when we reach this number, so when we reach the 15th, no, this is the 16th one, but that represents the 15th index, we update our data size and take it back from whatever we got it, and then we have to add 16 because obviously the previous 16 were the data that we don't actually needed. So we have to add that into it, and that's basically that's it. And then we for the next parts we just append it to our main byte array, which will contain our data, and then we return the byte array and then the file name. So now we have written the 2 functions, and let's write the rest of the code that will allow us to use this program from the command line. Now, a very good library that we can use is called argparser. So I will add these 2 libraries here. So I've added the math library and the argparse library. The argparse library will allow us to take some arguments from the command line and then parse it for us. So let me just copy the code from my previous example, and I just copy it because it's not super important, it's not really relevant to the logic part of the code. So just to save a little bit of time, I've copied it here. So the 4 things that we will be considering taking in account are the input file, the output file, and then we have 2 flags, D and E. D will represent if you want to decode it, and E if you want to encode it. Now, the first thing we need to make sure is that we have valid arguments. So let's first parse our arguments. So it will be args is equal to parser dot parse, and sorry, it will be parse args actually, args, and we will do that. And the first thing we need to take is the input file name, and we make sure that this is actually valid, is equal to args dot input file name. Alright, so and now we can make sure this is valid. So what we will be checking is if the file name is actually less than 12 characters, and this is because of the limit of the program. If you remember, when we were talking about the writing function, we reserved 12 bytes of data. So we need to make sure that it is within that limit. If the length of the input file name is actually greater than 12, then this would be invalid, and we will print that the input file name is larger than is too large, let's just say. and we will exit the program at that time. Then if this actually passes, we can also parse our output file name. So output file name is equal to args dot output file name. And now we have to do two things. We have two possibilities. Either we want to encode or we want to decode. So we will have two cases for that. Args dot encode and if args dot decode. And so in case we want to encode, first thing we need to do is take our image and convert it into a byte array. Sorry, convert it into a numpy array. So image is equal to image.open, and this will be image dot jpg, and we will convert it into a array, numpy dot array, and this will be image. And now we can we also need to make sure that the file that we're trying to encode is actually small enough that it can actually be encoded in the size of the image. So we can check what is the maximum size that this will support, and that will be max bytes size is equal to math.floor. I will do that because since we are dividing it, it might actually be an integer or something, so that's why I'm doing that. And image, so basically the width, the height, I think, multiplied by this is the shape. So the the height by the width, sorry, multiplied by the number of channels, and then this will be multiplied by 2 because there are two bits for every single byte of the image. So, and then we divide it by 8 because we want to get the number in bytes. And now we want to make sure that the size of the image is large enough. So we need to find the size of the file that we are trying to encode. So let's open the file. Open and input file name. And the mode has to be read binary, sorry, and as file, and we will read the content. So file contents is equal to file.read, and then we will check if the file size is smaller than the maximum size. So if length of file contents is actually greater than, so this has to be the length, sorry. If this is actually greater than the max bytes size minus 12, minus 16 actually, because we need 16 for the rest of the header. So if this is greater, that means that we can't actually fit it, and we will say that the file size is too large. File is too large, and then we can exit. And now we can actually, if we pass all of these conditions, we can continue with our main objective. So, which is write the data. That is a function that we just wrote, and we will pass the image, then the file contents, and then the input file name. And we will the image that we pass will be modified, and then we can just save it. So image, we need to first convert it into a image type, because this is actually a numpy array. So image dot from array, and pass in the image, and now we can save it. So image dot save, and we will have output file name, output file name, and plus bmp dot bmp. And as you remembered, that bmp is very important because we need to save it in a lossless format. Okay, now the other case is if you want to decode it. In this case, we can first, again, we need to read the image that is encoded with the data previously, and we will in this case have the input file name, and we need to convert it into a numpy array is equal to numpy.array and image, and finally we will decode it. So our function that extracts the data extracts the data in the file name and sorry about this, keyboard, extract data and image, and here we go. So this is this has been extracted, and now this data is the file that we can just save it. So we will open a file for writing, open file name, and now this time we have to write in binary format, and as file and file dot write data, and that should work. Let's try it. So we will open our folder. Let's just delete certain things. So I'm going to rename it just to have the dog. And we don't. This is the file that we just wrote. We don't need these images for now. And let's try to run it. So control C there. Yes, actually. Now let's. So we have Python encode 2.py. This is our new function, and we want to encode our dog image, and the output can be example. Sorry, of course there's no autocomplete for that. So, and that of course we need to also pass our flag of encoding, and input file name. It has no rx.input file name. 1 second. Let me just check quickly. So we have input file. Yes, that's true. It's not file name, it's just file. And this is output file. So that hopefully should solve it. And it has created it. So this is our new image. And again, just to show, I will delete this dog. And now let's try to decode it. So let's decode it, and we will be decoding the example.bmp. And let's see, it should, sorry, this one, the following arguments are required. Okay. So now it has actually recovered our data. So here you can see that's so the program actually works.